Welcome back to Genetic Algorithms. We have just discussed the mechanism of natural selection that comprises two steps. Step 2a, fitness function. According to Darwin, a strong individual is the one that fits better to the environment. What is the environment in our case? It's the problem we are trying to solve. To assess fitness, we'll create a function that quantifies how much a solution fits the problem, solves the problem. In other words, our function will quantify how good a solution is. We will use this function to attach a fitness score to each individual in the population. As said before, we expect these scores to be relatively low for now because random solutions won't yield good solutions. But then again, some will have better scores than others. Step 2b, biased selection. According to Darwin, it's not that only the most fit individual produce offspring. Rather, the more an individual is fit to the environment, the more chances it will have to win when competing on limited resources, such as food, the longer they will live, and therefore the more chances they will have to produce offspring. So now we will create a new population comprised of the offspring of parents from the former population. We will do so by creating a biased selection function that every time it's called, it picks a random parent out from the population, but in such a way that the chances a certain individual will be chosen as parent will be correlated to its fitness score and in comparison to the scores of all others in the population. For simplicity, the new population will have the same amount of individuals as the former population. And for each offspring in the new population, we will pick with the biased selection function 2 parents. Step 3, chromosomal crossover. Produce a sequence for the offspring by combining the sequences of its parents. One of the reasons eukaryotes have advanced more through evolution than prokaryotes is claimed to be connected to their sexual nature of reproduction, where the traits of 2 parents are combined together in some random manner, in a process called chromosomal crossover, which increases the diversity in the population and the natural selection mechanism. After we pick 2 parents in the former step, we will now produce an offspring, a sequence, by combining some parts of the sequences from its 2 parents. A trivial option is to select a random point on the sequence and take the subsequence before this point from one parent and the subsequence after this point from the second parent. There could be other ways to combine the sequences, but the main thing is that the traits get somehow combined. The rationale is that, as in nature, some offspring will be more or less the average of their parents, some will receive a bad combination of the weaker traits of the father with the weaker traits of the mother, and therefore their fitness score will be lower than both parents. However, a few offspring will be lucky enough to get combination of those better traits of the mother with those of the father, like happened to me, for example. I got my mother's smile and my father's ears, and luckily not the other way around. In some cases, the fitness score of the offspring will be better than the ones of both its parents. Step 4, mutation. Add random genetic mutations. The reproduction process will not be complete without the miracle of mutation. It is a miracle, as without the random errors that occur in replication and reproduction processes, without this diversity engine, life, as we know it, could not have evolved. The same applies here. Therefore, we will add a few random mutations to the sequence of each offspring. As in nature, some of them will actually be harmful, some will be neutral, but in some chances, a random mutation could be beneficial. We expect in this case that the fitness score of the offspring will be better than the ones of both its parents. In this case, we have a new population, a new generation, which will continue to go through natural selection. So we will go back to step 2, natural selection, assign new scores to all the individuals of the new generation, and then continue the cycle and create another generation and another generation and so on. We can rightly assume that over time, over generations, the individuals in the population will improve as the beneficial crossovers and mutations, together with the biased selection mechanism, will tend to strike roots and establish the population. What's so nice about computers is that we can set this process loose and create an evolution of thousands and even millions of generations quite easily. But every algorithm needs to stop and produce the required output. So when we will stop this process that potentially could continue forever? Step 5, stopping criteria. One criterion to stop could be if we reached an individual with the best possible fitness score. However, in many cases, we don't know what is the best possible score for the problem we are facing. So another very good criterion is to see when improvements becomes marginal or non-existent. This graph depicts the improvement over generations of the average fitness scores of the population and of the best fitness score in the population. As you can see, after around 300 generations, there is no substantial improvement for another 100 generations. It's a sort of convergence. When we spot something like that, we can stop the evolution process. As we have just seen, this is an example of how AI can find solutions to a problem instead of computing solutions. Does that make sense to you? Can you see how we make evolution of a solution to a problem? In the next segments, we will show it in action. First, we will go back to the clustering problem we discussed previously and see how we can implement a genetic algorithm, GA, that solves it. Then we will see a few famous examples of applications of GAs in general and in medicine in particular.